Good day, everybody. Justin Moore, College Physics here. We're going to look at some more aspects of rotation, and let's just get to it here. So I got a question for you. Take this point mass here. Let's say it's a point mass, highly localized, and I spin it around like this. I say, does that point mass have kinetic energy? Say, well, yeah, it's moving through space, right? It's moving, it has the velocity, it's the mass and velocity, and that substantiates some sort of kinetic energy. If I got hit with this, it would hurt, because it would be imparting its kinetic energy to me, and well, I don't really want that. Or I could hit something else with it, knock something over, do work, all sorts of stuff, right? But the main point is, yeah, it has kinetic energy. So what we want to start looking at is, well, how can we quantify kinetic energy of like extended objects, or objects that are ultimately composed of multiple point masses? So I can take this entire meter stick here, and I can start spinning around and say, hey, does this meter stick have kinetic energy? And you say, well, yeah, it's moving. Well, yeah, that's great. It is. It's moving. But different parts of it, different mass elements, if you will, are moving at different rates through space. This little orange mass element versus this little blue mass element are moving at vastly different rates through space as this rotates around as a rigid object. Everything's moving at the same angular velocity, but not at the same tangential velocity, not at the same rate through space. And that's what kinetic energy is really a function of, right? How fast is something moving? So what we want to start doing is looking at rotational kinetic energy. And generally, I just call it Ke sub r, so we know that we're talking about rotation with a subscript r in there. So consider a point mass. Rotating in a circular path. At a constant angular rate. We can just have some little axis of rotation. We'll take some point mass, I'll call it M1, and it is some distance from the axis of rotation. A distance R1. And this point mass here is going to be, not initial, but 1. We'll be rotating around this axis of rotation with a constant angular velocity, omega sub 1. We'll say, well, what is its rotational kinetic energy? Well, it comes down to this, right? It comes down to, well, how fast is it actually moving through space? This mass likewise has a tangential speed. Well, really, its kinetic energy is going to be 1/2 times the mass times speed squared, which is its tangential speed. So that's fine. That's just our old notion of kinetic energy, 1/2 mv squared. Let's write it in terms of the rotational quantity, though. Let's write it in terms of omega and r. Let me put a little subscript 1 there, so that we know. And what do we have? We have the tangential speed of this mass, M1, is equal to R1 omega 1. So we can write then that the rotational kinetic energy of this mass, M1, is then equal to 1/2 M1 times the quantity of R1 omega 1 squared. Fantastic. There we go. We got its rotational kinetic energy written in terms of the radius at which it rotates and its angular velocity. Remember we said constant angular velocity? It doesn't need to be constant. If it's not constant, that's the rotational kinetic energy is changing with respect to time. That's kind of distractive, if anything, at this point. So the main point is, yeah, we can quantify it in terms of rotational quantities. But what happens happens if we now have, instead of 1 point mass, 2 point masses that are rigidly connected? Now consider 2 point masses. Rigidly connected. We'll take some axis of rotation. We'll take some M1 like this, and attached to it, we have some M2. This is one rigid system here. We've got 2 different masses. We've got this one exists at a distance of R1, and then this distance we'll call R2. So that they're both different distances from this axis of rotation. We'll say, well, what is the total kinetic energy of this rotating object? What is the total rotational kinetic energy? Well, if we're looking for the total, it would be the sum of the individual rotational kinetic energies, right? We just say we got 2 objects rotating, and we just sum up what their individual contributions are. So we have that KE sub rotation total is going to be KER1 plus KER2, the rotational kinetic energy of mass number 1 plus rotational kinetic energy of mass number 2, which we can write out as 1/2 M1 V tangential 1 squared plus 1/2 M2 V tangential 2 squared. That's fine. The individual kinetic energies based upon how fast we're moving through space and the masses. And what else do we have with this? We've got that V tangential 1 is equal to R1 omega 1, and V tangential 2 is equal to R2 omega 2. And there's a little connection that we need to make here. If this is a rigid object, every point on it rotates at the same angular rate. Everything goes through the same angle in the same amount of time, so everything has the same angular velocity. Even though that we're saying there's 2 in omega 1 and omega 2, omega 1 is equal to omega 2 if the object is rigid. So we don't really need to make a distinction between those omegas if we're saying that, well, it's a rigid object. But there is a distinction to be made between the actual tangential speeds, right? We have V tangential 1, we have a V tangential 2. Which object's moving faster through space? The one that's furthest away from the axis of rotation, because it has a much greater distance, or a relatively greater distance, and it must travel in the same amount of time as this object as it sweeps through the same angle in the same amount of time. So, this is where rotation really necessitates that you take a close look at things. It's not just how fast the object's moving, because different points on the object are moving at different rates. So, we can go with this. We'll just go ahead and put in our V tangential 1 or our V tangential 2 here and there, and we can get that the total rotational kinetic energy of this system is going to be 1/2 M1 times the quantity of R1 omega squared. Don't need omega 1 there because they're both rotating at the same angular rate. Plus 1/2 M2 quantity of R2 omega squared. All right. So the nice thing about this, again, is that everything is moving to the constant angular rate, or the same angular rate. Not necessarily constant, but they exhibit the same changes in angular position with respect to time. Omega is the same for the entire rigid object. But depending on how far away the mass element is from the axis of rotation, really has something to say with how much kinetic energy that particular element has. The further away from the axis of rotation, the greater the contribution kinetic energy-wise that that particular mass element has. So again, we're just looking at 2-point masses, but we can still do this, right? What happens if I say, well, M1 and M2, those are two different mass elements with different masses. They are at R1 and R2, two different radial distances away from the axis of rotation, but have the same omega. Can we rewrite this a little bit? Well, I can factor out an omega squared, factor out a 1/2, and we can rewrite this as 1/2 multiplied by the quantity of M1 R1 squared plus M2 R2 squared multiplied by omega squared. The reason that we want to write it out like this is because, again, this quantity right in the middle here is what is dependent on the mass distribution, where the individual point masses are relative to the axis of rotation, and what those individual point masses are, how much mass. That's it. What happens if we have 3 masses? We stick on another one. Or 4, or 5, or 100, or a billion, or Avogadro's number. What are we going to do? Well, if we got 3 different masses at 3 different radii, we would end up having 3 different terms. We'd have an M1 R1 squared plus M2 R2 squared plus M3 R3 squared. 4 masses, we'd add on an M4 R4 squared, 5 M5 R5 squared. We just keep on adding things on, right? We get another term in here for every mass that we add into the system. And it really doesn't matter if we're lining them all up or putting something else over here with an R4, M4. As long as it's a rigid object, all we need to know is what is the mass element and how far away is it from the axis of rotation, and add that into this particular section right here. That's it. So what this allows us to do is actually write out rotational kinetic energy for a system of rigidly bound point masses rotating at an angular rate omega as this. So this middle term, let's write this down. For a system of rigidly bound point masses, rotated at a rate, or angular rate, omega, total rotational kinetic energy is just one we can write it like this. We've got ourselves K E sub R total is going to be equal to 1/2 multiplied by some sort of sum here, right? The sum of the individual masses, mass elements, times their radial distance away from the axis of rotation squared. Let's write that as the sum from I equals 1 to n of m sub I r sub I squared times omega squared. With this term right here, sum from I equals 1 to n of m sub I r sub I squared is just m1 r1 squared plus m2 r2 squared plus dot 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 plus m sub n r sub n squared. Tell us how many mass elements you have. That's how many terms you're going to have in there. We'll just write it in the summation notation. Well, we can define this as a certain quantity. Well, this is defined what is known as moment of inertia. I for a system of point masses, the moment of inertia is equal to the sum from I equals 1 to n of m sub I, r sub I squared, where m sub I and r sub I are what we just described, what the individual mass elements are, and at what radial distance away from the axis of rotation they reside. Which really depends, right? Depends on where you say your axis of rotation is. So this is something you've got to be a little bit careful of. But nonetheless, we can define this quantity, moment of inertia, and note that then KE rotation total will be written as 1/2 I omega squared, which is very much like 1/2 mv squared, but this is for rotational kinetic energy. Object rotating with an angular velocity omega has some sort of kinetic energy with respect to the mass elements rotating around some axis of rotation, substantiating some moment of inertia of the object. This is really a measurement of the distribution of the mass relative to the axis of rotation. That's what moment of inertia is. And it's necessitated by looking at extended objects or objects with more than one localized mass under a rotation. And it happens to be a really important quantity. And very often it is confusing to people. But you've got to kind of get used to it and understand it's just really a matter of where are all the mass elements and, where are they? Where are all the mass elements relative to the axis of rotation, and what are their individual masses in terms of their compartmentalization, if you will. So in the end, you think about any mass, right? Got this extended object. This is just a bunch of point masses, a bunch of protons and neutrons and electrons, all highly localized at different positions, and depending on where I rotate this, those individual mass elements are different radial distances away from this axis of rotation. I rotate it from the middle, I've got a different mass distribution relative to that axis of rotation. So what you have to be careful of is, again, what is your axis of rotation when you're defining an object's moment of inertia? It isn't something that just a matter of the object. It's a matter of what point in space are you measuring it with respect to? And for us, we're measuring it with respect to an axis of rotation. So that is a nice quantity. Units. SI units of a moment of inertia, what do they have to be? Well, we go back and look. It has to be mass times radius squared. So we got kilogram meter squared. And there's the SI units of it, and that's really it in terms of a system of point masses. So that's what we wanted to look at. We'll be back. So, what if we don't have point masses? Or we can start to consider extended masses that are continuous mass distributions, which is really not true because, like I said, everything's made of a bunch of highly localized protons, electrons, neutrons. But if we can consider things to be sort of continuous because there's just so many of them packed in, then we can start to develop other ways of determining what moments of inertia are for some common types of objects. So in order to do that, that involves a little bit of calculus. So I'll split that into another segment and just note that generally for the problems that we're looking at, you just need to go look up what the object's moment of inertia is relative to its particular axis of rotation. So, look at common objects. Moments. Common objects, moments of inertia. About their center. So we start looking at something like, if we have a wheel here. Well, the wheel has some sort of fixed axis that's in the center here, and everything rotates about that. Now this could be a solid wheel, like a solid cylinder, or it could just be this little strip here in the end that we consider, like a hoop, or it could be something like a ball that's rolling, a sphere, rolling about its center. And those are the general types of objects that you'll be dealing with and have very well-defined moments of inertia. So I'll just tell you what those are. I'm not going to derive them here. I'll show you what one of them is that's easy to figure out without any calculus, but just something that you're going to use from time to time. Some of these problems, you're just going to know what they are. So look at I for a solid cylinder. For a solid cylinder, moment of inertia is 1/2 mr squared. M is equal to the total mass, and r is the radius. And again, this is about its center. So we've got ourselves a cylinder, and we're looking at, well, it rotating about its center, like a CD or a wheel, something like that. Solid cylinder. We've also got a hoop, a cylindrical ring, hoop, or ring. That ends up being just m times r squared. Again, m's the total mass, r is the radius. So we find that a hoop that has the same radius and same mass as a solid cylinder has a greater moment of inertia. Ask yourself, why would that be? Grab something really quick here. I've got two things right here. These actually have right about the same mass. Seen Mr. Happy Face before? And they have about the same radii as well. Relative to their centers, which they would roll about, if allowed to roll, you probably couldn't see that, but it rolls, right? Rolls about its center. This one has a greater moment of inertia. Why? Because all of its mass, all of its individual mass elements are as far away as they can be from the central axis of rotation. Whereas for this one, we have the same amount of mass elements, but there's a spread. Some are as far away as they can be, some are really close. Again, for point masses, the moment of inertia depends on this heavily, how far away the individual mass elements are away from the axis of rotation. So if it turns out that moment of inertia for a solid cylinder is less than the moment of inertia for a comparable hoop or ring. So those are two that you'll deal with quite a bit. You've also got solid sphere. The moment of inertia of a solid sphere is equal to 2/5 mr squared, and a spherical shell, much like a ball that has a very thin shell on it, is equal to 2/3 mr squared. These are all considered about the very center of the object itself. So those are some common moments of inertia that you'll run into. We can actually get this one pretty easily. So for this hoop here, we can take some central axis and let's try to draw a real circle. Looks good enough. So there's a circle. We say that there's our axis of rotation, and we have that all of the mass elements have the same radii. So we can even consider this to be made of a bunch of little mass elements all packed together. Not even treat this as continuous, treat it as truly a thin layer of these mass elements all separated by. So we've got M1, 2, 3, 4, 5, 6, 7, 8, M8, and we go all the way around, and well, however many mass elements we break this up into is how many we've got, right? So if we look at the moment of inertia of this, we have that it is going to be equal to the sum from I equals 1 to n of m sub I, r sub I squared. Well, r sub 1 is equal to r sub 2 is equal to r sub n. Every mass element is the same radial distance away from the axis of rotation. So this is just one value that we're summing up over. So that one kind of just gets pulled out. So we can write this then as I is equal to r squared multiplied by the sum from I equals 1 to n of m sub I. So what happens when we sum up all the individual mass elements? Well, this is going to be equal then to r squared multiplied by m1 plus m2 plus m3 plus dot 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 plus m sub n. What happens when you add up all the individual mass elements? That's the total mass, right? And this is going to be equal to m r squared. That's just the total mass. So there you go. There's this cylindrical hoop, or a ring, if you will. This moment of inertia extracted out pretty easy just by directly looking at the fact that everything has the same radial distance. Do that for the spherical shell too. A little bit more tricky, but not that bad. And that's it. The other ones, generally, you need to be able to employ some calculus to add up the variation of the radial distances. But at any rate, those are some common ones that you'll utilize. So read things carefully and use them. All right, good stuff. All right, everybody, we want to look at a little problem now involving some rotational kinetic energy. We'll also consider not just rotational, but translational as well, which is our linear type of kinetic energy. So consider this. I take some object and I say it's spinning around, right? It has some rotational kinetic energy because of all its little mass elements at different locations are moving relative to the axis of rotation. So I take the moment of inertia of the object, that's fine, 1/2 I omega squared, and I figure out what its rotational kinetic energy is. But what happens if I have an object that's actually translating its rotation into linear motion? It is both rotating and moving forward. Let's just think of the moving forward part. This object moves forward as a whole at one rate, whether I'm dragging it across this or whether it's actually rolling. The whole object's moving. Total mass is moving at one velocity, or all the mass elements are moving forward at one velocity as a whole. And then we have all the individual mass elements rotating around, having their different rotational velocities, or not rotational velocities, but rotational kinetic energies. So when we start talking about rolling objects, the object has both translational and rotational kinetic energy. So we just want to appreciate that object under translation can have two different types, in a sense, of kinetic energy. And still manifestations of all moving parts really moving around. So let's just take a little look at a problem that involves some rotational and translational kinetic energy, and we'll go from there. So we're going to take ourselves a solid sphere that has a particular radius and look at it rolling across the ground and ask some questions about it. So here's the problem. All right, so we've got ourselves some level ground here, and we're going to take ourselves a solid sphere. It has some radius, and it is going to have some angular acceleration, let's say that that is 3 radians per second squared, and then it was initially at rest. And we note that this is a solid sphere. And what do? Well, we need its moment of inertia if we're considering anything regarding rotational kinetic energy. So we know that I is equal to, we look it on up for a solid sphere rotating about its center, which a rolling object does, will be 2/3 mr squared. So let's say that the mass of this object is 2.50 kilograms, and that the radius of this object is 0.350 meters. It's initially at rest, undergoing an angular acceleration of 3 radians per second squared. We just asked some questions. So the first question was, what is the rotational kinetic energy at t equals 4 seconds? Okay, the cell rotation evaluated at t equals 4 seconds is equal to what? Well, we just go ahead and figure out what we need to know. We know that the rotational kinetic energy is 1/2 I omega squared. I, for this given object here, rotating about its center, is this 2/3 mr squared. That's constant. 1/2 constant. This is what's changing with respect to time, right? The angular velocity based upon the angular acceleration. So we've got that omega final is equal to alpha t plus omega initial. So if we wanted to, we could write this out and say that k e sub r as a function of time is going to be equal to 1/2 times 2/3 mr squared multiplied by omega squared, where that is going to be alpha t plus omega initial quantity squared. So while that looks sort of big, it's really not, because this reduces down to really not that much. So number one, omega initial is equal to 0. 2, we can get rid of this 1/2 times 2/3 and just call it 1/3, and we are left with this. This is now 1/3 mr squared times alpha t quantity squared. Make that, everything else kind of falls into place. And there we go. So what do we want to do? We want to evaluate this at t equals 4 seconds. So this is going to go to 1/3 multiplied by 2.5 kilograms multiplied by 0.35 meters quantity squared multiplied by the quantity of 3 radians per second squared times time of 4 seconds. It's that whole thing squared, which gives us the rotational kinetic energy evaluated at t equals 4 seconds to be, whew, one sec. Gotta get used to this calculator. 0.35 squared. Then I have to go over. Okay, 24 squared times 9 times 16. 14.7. 14.7 what? That's right, joules. This is kinetic energy. So 14.7 joules of rotational kinetic energy after 4 seconds goes by. All right, so what about the translational kinetic energy? What is kinetic energy of this object at t equals 4 seconds, translationalized? So we want this, t equals 4 seconds. Well, that is just going to be equal to 1/2 mv squared, evaluated t equals 4 seconds. So we need to know how fast is this object moving forward at t equals 4 seconds. This is translational velocity. That's it. So we know that v is equal to r omega through equations of a translation. So we can go ahead and figure out what that is, either in terms of omega or v. It doesn't really matter. Let's just use ourselves omega because we already got the r, the radius, and we know what the angular acceleration is, because omega final is equal to alpha t plus omega initial. So we can write this as being equal to 1/2 m times v squared, where v is equal to r times omega. So we've got R squared times omega squared, which is then, break this up. It looks so. Omega final squared, which is then equal to 1/2 m. This would really be a capital R here. Radius of it, 1/2 m r squared times omega final squared, which is alpha t quantity squared. So again, alpha is just 3 radians per second squared. T is equal to 4 radians per second. And we get ourselves 0.5 times 2.5 times 0.25 squared times 9 times 9 times 16. And we get ourselves 22.05. 22.05 joules of translational kinetic energy. So, there we go. We got this. What else can we ask? Hey, how about this? C, what is the total kinetic energy at t equals 4 seconds? Well, the total kinetic energy is just the sum of the rotational and translational. So this is going to be equal to Ke sub r evaluated at t equals 4 seconds plus Ke sub t evaluated at t is equal to 4 seconds, which is merely just our 14.7 joules plus our 22.05 joules, which is what, going to give us 36.75 joules of total kinetic energy after 4 seconds has gone by. So not that bad, right? Could have just asked that in the very beginning, quantified what each of these terms are, and there we go. It's nice to be able to see that we can break it down into the individual pieces, if you will, of kinetic energy, rotational and translational. But here's another question. Hey, at what point in time will the total kinetic energy of this object be equal to 75 joules? So we need to figure out when is the total kinetic energy equal to this. So what do we have? Well, we've got ourselves that 75 joules must be equal to the sum of the translational and the rotational kinetic energies. So we got a Ke sub t plus a Ke sub r. Well, we know that this is 1/2 mv squared plus 1/2 I omega squared. And we can start opening some things up. We know that V is equal to R omega, so we can go ahead and put that in there. Let's write this out. 75 joules is equal to 1/2 m R omega quantity squared for the V squared plus a 1/2 I omega squared. Just leaving I how it is just for right now. And what we notice about this, they both have a nice common factor. That common factor being omega squared. What does that mean? Well, omega is what holds the time dependence in it, right? We know that omega is going to be alpha t because omega initial is equal to 0. Omega is a function of time. So there's the time right there. We got to be able to isolate that. So let us expand some stuff out. We can group some terms and kind of see what we can do with this. So let us write this as 75 joules is equal to 1/2 m r squared multiplied by alpha t quantity squared, so r squared, then omega squared, plus a 1/2 times 2/3 m r squared times omega squared, which is quantity of alpha t squared. So a lot of this stuff is going to collapse down, right? Because we've got a common term of m and r squared and then alpha squared, all things that we know. And then we can factor out the t squared. Move everything to the other side, and have some nice final expression there. So let's collect some terms here. We can make this 1/3, and then we've got a 1/2 mr squared plus a 1/3 mr squared times alpha squared quantity times t squared. Okay, let's write this. 75 joules is equal to the quantity of 1/2 mr squared alpha squared plus 1/3 mr squared alpha squared, factoring that alpha out, times t squared. Factor the t out there because that's what we want to isolate. We want to figure out the time that that occurs at. Look at everything is the same in nature. You have 1/2 of something plus 1/3 of something. That something being mr squared alpha squared. So what can we do here? We can call this 3/6 and 2/6, 5/6, 1/3 and 1/2. 5/6 mr squared alpha squared times t squared, 75. So 75 joules is equal to 1/3 plus a 1/2. We got 3/6 plus 2/6, which gives us a 5/6. So we can write this as 5/6 mr squared alpha squared t squared. We want to solve this out for t. Let's just do that. I had a little problem with video back though. So we have that, again, 75 joules, it's 5/6 mr squared alpha squared times t squared. We can go ahead and solve this up for t. 6 times 75 times 5, divided by 5 times 2.5 mr squared alpha squared. Square root of all that, and we get our nice value, 5.714 seconds. That is the time at which the total kinetic energy of the object is 75 joules, compared to t equals 4 seconds when it was approximately 36 joules. It's not much more time, right? So about 1.7 seconds goes by, and it increased its kinetic energy almost twofold, almost doubled it, really close. What's with that? We got to remember that the kinetic energy itself is dependent on how fast this object's spinning around. Because how fast it moves forward depends on how fast it's spinning around. And, well, that is that it depends on it squared. But the rate of the change of the angular velocity is linear. So it's not one-to-one. We don't get a linear relationship with respect to time and kinetic energy. It varies as omega squared, ultimately. So there you go. There we go. All right. Have a good one.